Good morning, everybody. It's Miss Manili, and I'm sorry I can't be with you today. I did want to leave a video, though, so that you didn't fall any further behind from the snow. And so today's tutorial is going to be about the sampling distributions for sample means. The sampling distribution for a sample mean is very similar to the sampling distribution for a sample proportion. The differences really lie in the conditions for which you can use a normal curve and also the mean and the standard deviation that we use for a normal curve. So I'm going to skip over the warm-up today, and we'll do the warm-up next class when I'm back. And I'm just going to talk to you a little bit about the different outcomes for this afternoon. So first of all, we're going to be able to find the mean and the standard deviation for the sampling distribution for a sample mean. The 10% condition for calculating the standard deviation is actually the same for the mean as it is for the proportion. And basically that just means that our population has to be at least 10 times the size of our sample. And I'm using my notebook at home, and so my handwriting isn't quite as nice on this as it is when I use the smartboard. But this condition that we're talking about is essentially that the population is at least 10 times our sample size. And so that's the formula that we use in order to use any of the standard deviations. We'll also talk about how the shape of the sampling distribution is going to be affected by not only the shape of the population, but also the sample size. And we've already done some investigations like this before, but it's very similar to the relationship that you saw with the sample proportion. And then finally, if it is appropriate, we'll use the normal distribution to actually calculate probabilities. Okay, so you should have some notes and some things to fill out as we go. Sample proportions and means. So sample proportions are going to arise when we're dealing with categorical variables. We examine the proportion of a sample that exhibits a certain characteristic. So essentially, this is the binomial scenario. If the characteristic of interest, if we call that a success, then all other characteristics, whether there's 1 or 12 of them, are going to constitute a failure. And so as long as you can identify what we would call a success in a binomial scenario, we can look at the proportion of successes in our sample, and it becomes a proportion. And then whatever the true proportion is for the population is what we call P, and what we call the proportion in our sample is our P hat. That would be the proportion of successes in our sample. When we're dealing with quantitative variables, though, for example, like income of a household, diameter of a bearing, the blood pressure of a patient, we're not interested in a proportion anymore. We're interested in things like a mean or a median, or perhaps the standard deviation. In this course, we're going to focus on means, though. That's going to be our statistic and our parameter of interest when we're dealing with quantitative variables. But just know that if you were to pursue, other courses in statistics, you could also look at sampling distributions for a standard deviation or a median. But in this course, we focus on proportions for categorical variables and means for quantitative variables. We're also going to look at the difference between two proportions, or the difference between two means. In the case of, for example, if we're doing an experiment and we've got a control group and an experimental group or treatment group, and we want to compare the difference in weight gain or weight loss, or perhaps test scores, we can look at the difference between the two. All right, we've seen some examples like this already with the proportion, but if we were to consider the population of household or mean household earnings, so if I were to look at this graph over here represents a population. So if I were to look at a population, and it doesn't tell us what population this is, if it's a certain city or if it's the United States or whatever, but this graph right here, this histogram, gives us the population distribution. So if I were to ask every household, what their median income, or in this case, I guess it's the mean income, this is what the histogram would look like. And we're familiar with that incomes tend to be skewed to the right because you have those crazy rich people that kind of fall outside of where the rest of us live. Now, if I were, instead of looking at my entire population and looking at one individual at a time, if I were to take a sample of size 100 and ask all of those individuals what their household income was and then find the mean and do this repeatedly, this is what the distribution of sample means would look like. So this is just repeatedly gathering samples of size 100 and finding the mean household income. And you can notice that there's quite a difference between my sampling distribution, that's what this is. And again, I apologize that my handwriting is so bad on this thing. This is the sampling distribution of the mean income for samples of size 100. And so you can notice that obviously my population, even though it was skewed to the right, the sampling distribution is bell-shaped and symmetric. We had a center here that looks to be, I don't know, maybe like around $75,000. And if you look at this distribution, notice that the mean is also around $70,000 or $70,000. This is an indication that my sample mean is an unbiased estimator of the population mean, and that's what we want. We want to know that we're taking representative samples. The other thing that we'd want to compare is the spread, and you can obviously see that the spread for the population goes from like 0 to about 250,000, whereas the spread for my samples goes from, it looks like, about 50,000 to about 100,000. And that's because if I'm looking at a sample of 100 people, those crazy rich people are going to get absorbed in with the rest of the population when I take a mean. So those individuals that make so much money, when I average them with someone who maybe doesn't have an income and not someone who's unemployed, it's going to balance out. And so my extremes are going to get absorbed into the center. And so when it asks you to, what do you notice about the shape, the center, and the spread of each, we can see that the shape of the sampling distribution is going to be more bell-shaped and symmetric. The center is exactly the same, or it should be if it's an unbiased estimator, and the spread is going to be smaller. Okay, so this leads us to talk about the sampling distribution for any sample mean, not just a sample mean of incomes, but for any sample mean. When we choose many simple random samples, and again, we have to make sure that the sampling technique that we're using is fair and representative. Otherwise, we're going to have bias, and we don't want that. But if I'm taking many, many simple random samples from a population, and I'm plotting them, if I'm plotting the mean, then the sampling distribution of the sample mean is going to be centered at the same place the population mean is, but it's going to be less spread out. And so we have a couple formulas that we can use. The center of my sampling distribution, I'm going to call it a mean since it's going to be bell-shaped and symmetric. I want to use the mean. So the mean, and notice that I'm using a subscript now. The mean for my sampling distributions of means is going to just be whatever the mean of the population is. If you remember when we were dealing with p hat, the mean of p hat was equal to the proportion in the population, whatever the true population proportion was. Well, now I'm dealing with means, so my mean for my sample mean, I know that sounds kind of redundant, is just the mean of the population. The standard deviation, we know, is going to decrease as my sample size increases, and so the standard deviation for my sample mean is just going to be whatever the standard deviation of my population is divided by the square root of n. And we saw that with p hat also. The standard deviation of p hat, I didn't use subscripts last time, is just going to be the square root, and it's p times 1 minus p over n, and all of that was underneath the radical. So even with the sample proportion, I was still dividing by the square root of n. Now, as with the sample proportion, the only time I can use this standard deviation formula is if the population is at least 10 times the size of my sample. And sometimes you don't know the entire population, so you'll actually have to make an assumption. Assume the population is at least 10 times whatever your sample size is. And so that characteristic is the same for both. So regardless of the shape of my population or the size of my sample, the mean is going to be whatever the mean of the true population is, and the standard deviation is going to be the standard deviation of the population divided by the square root of n. And that's as long as the population is at least 10 times the size of my sample. But what about the shape? That's the next step. What about the shape of my sampling distribution? We saw that with p hat, I could say that p hat was normal. And again, our parameters were p and then the square root of p times 1 minus p over n. I could say that p hat was normal as long as n times p was greater than or equal to 10 and n times 1 minus p was greater than or equal to 10. That was the condition that needed to be met in order to use a normal distribution for p hat. So we don't have a proportion this time, so I can't multiply n times p when I'm dealing with a mean. So we have to have a different requirement. And we do need to understand the shape of the sampling distribution. And it's going to depend on two things. It is going to depend a little bit on the shape of the population, but it's also going to depend mostly on the sample size. And that was true for the proportion as well. Okay, well, let's start with a normal population. So suppose that the population I'm dealing with is already normal. So, for example, I'm dealing with the heights of young women here, and I know that the mean, and I know this population is already normal, that is known. I know the mean of this population is 64.5, and I know the standard deviation of this population is 2.5. What we're going to find out as we get a little bit further into this course is that oftentimes we don't know the mean and the standard deviation of the population. If we did, we wouldn't really need to take a sample. So these values that were kind of given in these problems are just kind of helping us lay things out and lay out a process. We're actually going to have to adjust our distribution in the coming weeks because, like I said, it's not really practical to know in a real practical setting. We don't always know the mean and the standard deviation. Okay, so anyway, this yellow curve here, this is our population. And so if I'm considering all young women and their heights, this would be what the distribution would look like. This is my mean here, and we know that already is 64.5. So these graphs that you see on the bottom of the page are simulations. So the first is essentially if I were to take two women out of this population and find their average height and plot it, I might get a value there. If I do this again, I might get a value there. If I do it again, I'm going to get a value there, and again and again and again. So what you're seeing in this blue graph is a simulation of samples of size 2 over and over and over again and plotting all of the sample means. And what you should see is that the distribution continues to be bell-shaped and symmetric, just like the population. It's still centered around the same value as the population, but it's a little bit less spread out. And then notice as my sample size increases to, say, 30, that my distribution for sample means, that's what we're looking at in blue, is even more bell-shaped and symmetric. It's still centered right where the population mean is, and that should be true if it's an unbiased estimator, if I've done a simple random sample. And notice how much less the spread is. And so that's important to note. So if I'm pulling from a normal population, then regardless of my sample size, even if I pull a sample of size 2, we could still see that the sampling distribution was still bell-shaped and symmetric. So if the population is normal, regardless of the sample size, X bar is going to be distributed normally as well. And we'll just use the mean and the standard deviation formulas that we had on the previous slide. Okay, so if the population is normal, then I know X bar is going to be normal. It doesn't matter what the size of my sample is, but again, this criteria to use the standard deviation formula is that basically the population still has to be at least 10 times the size of my sample. All right, but what about if the population isn't normal? What I'm going to do is I'm going to go through the same exercise, but I'm going to do it with various shapes of different populations. So this first example, and I don't think you have this on your paper, this first example is a uniform population that takes on values from -3 to +3. So obviously the center is going to be here at 0. And so this is what the population looks like. The population is in yellow. If I start taking a sample of size 2, notice that my sampling distribution, or the simulation of it, is no longer uniform. It's looking like it's bell-shaped and symmetric. And as my sample size increases, you can see that by the time I get to a sample size of 30, the distribution is very clearly bell-shaped and symmetric. It's still centered at the same place, the population is centered, and the spread is much less. And that might make a little bit of sense because it's a symmetric population to start with. But what about if my population is skewed? So this would be an example. I'm trying to think of something that would be skewed to the left. Maybe the test scores on a really easy test where most people did really, really well. This would be a distribution that could be skewed to the left. So if I'm looking at an entire population, and then the graphs in blue represent my samples. So notice if I take a really small sample, the sampling distribution is still slightly skewed. Even a sample of size 5, it's more bell-shaped and symmetric as before, but it's still a little bit skewed. It's not until I get really up to like 30 individuals that the distribution is more clearly bell-shaped and symmetric. So this indicates that with large samples, even if my distribution for the population is skewed, the sampling distribution is going to be bell-shaped and symmetric. It's still centered. Notice that red line is the center. It's still centered around the population mean, and the spread is less. So that is still the same pattern that we've been seeing. Here's another example where we have a bimodal population. And so maybe we're looking at ages of people in a children's theater where you have a lot of young kids and then a lot of adults that have taken them there. And so we're looking at the distribution of ages. So we have a high frequency for young kids and we have a high frequency of people that are older. So this would be the population, and I didn't go through all of the simulations. I just wanted to show you what the graph would look like if I took a sample of size 30. So if I take a sample of size 30, I don't know if that surprises you or not, when we had, you know, the highest frequency in low values and in high values, when they average out, we're still in the middle. And so even a bimodal situation like this, the sampling distribution is bell-shaped and symmetric. It's still centered at the population mean, and the spread is less. And that is true for all of those scenarios. So when we're sampling from a non-normal population, and most distributions aren't normal, it's a remarkable fact that as the sample size n increases, the distribution of the sample means changes its shape. It looks less like that of the population and more like that of a normal distribution. When the sample is large enough, and we'll define what large enough means in just a second, the distribution of sample means is very close to normal no matter what the shape of the population is, as long as the population has a finite standard deviation. And this fact is known as the central limit theorem. So here's another example. This is I'm not sure what the population is measuring in this case, but it says this is a population distribution from Rice University. So this is the population. I don't know what we're measuring here, but you can see it's a very unusual shape. I don't know really how to describe it at all, except that it's atypical. Well, this is what the sampling distribution would look like if I took samples of 2 people and found their average. This would be what would happen if I took samples of 5 people and found their average. This is 10, and this is 25 people. So even from this really unusual population, I can't even really tell you what the shape of that graph is. Even as for a sample as small as 25, the graph of my sampling distribution still looks bell-shaped and symmetric. It's still centered around the same value as the population, and the spread is less. So that is the same for all of them. And this is known as the central limit theorem. So as the previous example illustrates, even when the population distribution is very non-normal, the sampling distribution of the mean, x bar, is often going to look approximately normal as long as the sample size is large. So we're going to still use the normal distribution, and what we mean by sample size being large is that n has to be over 30. So remember, with the population proportion, or when we're looking at the sampling distribution of proportions, we had to look at the relationship between n and p and n and 1 minus p, and both of those values had to be over 10. With x bar, we just have to have a sample of at least 30, or we have to have a population that's normal. And sometimes you're not told whether or not the population is normal. Sometimes it's something that you have to actually assume. So if it doesn't say in the problem and you have a small sample, you'll have to say, assuming the population is normal, x bar will also be normal with a mean of mu and a standard deviation of sigma over the square root of n. All right. And so these are just some characteristics of the sampling distribution of x bar. We saw a graph very similar to this with p hat. So the sampling distribution of x bar is the distribution of values of x bar in all possible samples of the same size from the population. The behavior of x bar, like p hat, is very similar. We know that the sample mean x bar should be an unbiased estimator of the population mean. So that's why it's really important to make sure that you're taking simple random samples or samples that are very representative of your population. When you're doing an experiment, you want to make sure that you can control for all of those other unwanted variables, and that you use randomization. Otherwise, your results are going to be biased. The second characteristic is that values of x bar, when I'm taking means, they're going to be less spread out than for larger samples than they would be for smaller samples. The standard deviation is going to decrease at a rate of the square root of n. So basically what that means is if I want to cut my standard deviation in half, I'm going to need to take a sample that's 4 times as large as my sample to cut it in half. And that's because if you think about it, so if my standard deviation for x bar is sigma over the square root of n, and I want to cut it in half, well, to get the 2 underneath the radical, that would be the same thing as having sigma over the square root of 4n, because the square root of 4 is just 2. And so you can see I'd have to multiply my sample times 4 to cut my standard deviation in half. And again, we only want to use the standard deviation formula when our population is at least 10 times the size of our sample. And that's most often going to be the case. You just have to write it on your paper when you're doing a problem. And so before we get into any examples, let me actually just summarize this. So I'm going to type it because my handwriting is so bad. So when we're looking at the distribution of sample means, so distribution, or let's take a look at our distribution for sample proportions first. This is what we did the other day. Increase the font size a little bit, maybe a little bit more. Okay, so this is going to be distribution of sample proportions, and then I'll have my, over here I'll do a distribution. Is that changing? Let's say distribution of sample means. Okay. And so this is X bar. And this is P hat. And I'm just going to spell it out because it's easier. Okay, so the sampling distribution of P hat. So I know that the mean of P hat, I'm going to have to write this actually. So the mean of P hat, we know, is going to be whatever the true population proportion is. And I know the standard deviation for P hat is going to be the square root of P times 1 minus P over N. And I can only use this formula when the population is at least 10 times n. That's the only time I'm allowed to use this formula. And that's usually something that we have to assume, but you do have to write it on your paper. So this gives us the center. This gives us the spread. We still need to know the distribution. We need to know the shape. And I can say that P hat is normal with these parameters, P and the square root of P times 1 minus P over N, as long as N times P is greater than or equal to 10 and N times 1 minus P is greater than or equal to 10. When we're dealing with sample means, we're going to have the mean of X bar. Again, it's just going to be whatever the true population mean is. And the standard deviation for X bar is going to be whatever the standard deviation is in the population divided by the square root of n. So these values have to be given to you in the problem. We're going to find, like I said later, is that a lot of times these aren't known, and so we have to work around that. And just like with the proportion, the only way that I'm allowed to use the standard deviation formula is if the population is at least 10 times the size of the sample. And so again, this gives me the center, this gives me the spread, the shape, the distribution itself, X bar is going to be approximately normal with a mean mu and a standard deviation of sigma over the square root of n. And there are two conditions. As long as either the population is normal, and again, that might be something you have to assume, and I'll talk about when it's appropriate to assume that in just a second, or n is greater than 30, greater than or equal to 30. So when is it appropriate to assume a population is normal? There are a couple criteria, or a couple things that we talked about at the beginning of the year, if you can remember. If you're dealing with like biological measurements, so temperature, height, blood pressure, most of those kinds of things, if I'm calculating these values from a population of individuals, I'm going to see a normal distribution. Other things that we can assume to be normal would be standardized test scores. If I'm talking about the SAT, even if I don't describe in the problem that the population of SAT or the distribution of SAT scores is normal, because it's a standardized test, you can assume that the population is normal. Repeated measurements. If I'm looking at a production process and I'm weighing ball bearings, I can assume that the population of the weight of those ball bearings is going to be normal. Okay, so those are times when it's appropriate to assume the population is normal, even if it doesn't say so in the problem. Other times, you know, if it's a free response question on the AP exam and there's like 5 parts to it, and the very first question is asking basically what the distribution is for X bar or P hat, you might want to just go ahead and say, if we assume the population is normal, then we can use the sampling distribution for X bar and say that X bar is distributed normally, and then continue with the problem. Because as long as you put the word if the population is normal, then we can assume these things. Then you're covered. You're still showing that you understand the statistics, you're explaining that you understand the conditions, and you're proceeding through the problem. I would not, if you're given a 5-bullet question and you tell the readers in the very first bullet, I can't assume this population is normal, and so therefore I can't continue. I mean, they're obviously putting those questions down to get you to answer them. So don't leave anything blank. If you have to make an assumption, state it. Okay, you're given several examples. I'd like to go ahead and do the first one with you, and then I'd like you to press pause and do the rest as a class. You can work with a partner, and then I'll go ahead and post the answers too so that you can see. In the first one, it says the height of young women varies approximately according to the normal distribution. Remember, the 64.5 is our mean, and the 2.5 is our standard deviation. If we choose one young woman at random, then the heights we get in repeated choices will follow that distribution. That's what that distribution means. So letter A is saying define the mean and the standard deviation of the population of heights of young women. Well, we're given that. We know that the mean is 64.5, and I know the standard deviation. This is not the sampling distribution now. This is the population that we're talking about. And if I want to know the probability that a woman selected at random is over 68 inches tall, this is the probability that we calculated first semester. If I say that X equals the height of a woman, don't have a lot of space, so I'm just going to be abbreviating, then I'd say that X is distributed normally with the mean and the standard deviation that are given. So in terms of my notation, when I'm finding the probability, I'm just finding the probability that X, make sure you're using X and not P hat, that X is greater than 68. And remember, with a normal distribution, because it's continuous, it doesn't matter if we include the equal sign or not. It's not going to change our probability. Now, on the AP exam, you are required to change this to a Z-score. And so let's just go ahead and do that, even though it's annoying. And I did double check with some other teachers that have actually been through the AP grading process, and you will lose points if you don't change to a Z-score. So let's just review how to do that. We take our original observation, 68, and we subtract the mean, 64.5, and then we divide by the standard deviation, 2.5. And that gives us our Z-score, which is 1.4. So I'm going to say Z is now greater than or equal to 1.4. And so when I'm using my distribution, remember we always use a normal CDF. And there's 2 ways you can do this. If you want to talk in terms of X, you can. I'm going to do it both ways just to remind you how to do it. Remember, the normal CDF is different than the binomial. With the normal, we put a lower bound, then an upper bound, then the mean, then the standard deviation. And I have, on my computer, I have the older version of the calculator, so I have to put it in as a string of commands. If you have one of the new ones, it kind of prompts you, which is nice. The lower bound in this case is 68. My upper bound is infinity, so I'm just going to do 99999. The mean, since I'm dealing with 68, I need to deal with the mean of X, which is 64.5. And my standard deviation is 2.5. Okay? And that's what I get. If I want to do the same thing, but in terms of Z, so I'm going to choose a normal CDF, but this time I'm dealing with Z. My lower bound is 1.4. My upper bound is still infinity. But this time, the mean and the standard deviation are 0 and 1. And if you have one of the older calculators, you don't actually have to type in 0 and 1. It's a default setting. So you can just put a lower bound and an upper bound. And notice you get the same probability. Okay, so that's the probability of selecting a single woman who's over 68 inches tall. Well, in part B, it's saying now we're going to look at simple random samples of 10 women, and then we're going to find the mean of the group. So what are the mean and the standard deviation for the sampling distribution? So now we're talking about X bar. So X bar now is the sample mean. I'm not talking about a single X. I'm talking about the average in my sample. And I know that X bar is going to have a mean that's equivalent to the population mean. And let me put a subscript just to separate them. Sorry, I know it's hard to see. And my standard deviation for X bar is going to be whatever the standard deviation was in my population, 2.5, over the square root of 10. And I'm just going to actually leave that there. And so now if I'm trying to find the probability, the next question then would be, can I assume that this distribution is normal? And in this case, my sample is actually pretty small. Remember, it needs to be over 30. Or the other criteria is that the population is normal. And so since the population is normal, I know X bar is normal. Sorry, I know this was hard to say. So X bar is normal because the population is normal. So you do have to say this. You do have to explain what distribution you're using to calculate any of the probabilities. And so if I'm trying to find, this time I'm finding the probability that X bar is over 68. And you can put an equal sign there or not. It doesn't really matter. And so again, I want to change this to a z-score. So again, it's going to be 68 divided by, oops, not divided by, what am I trying to do? 68 minus the mean, which still is 64.5. And I'm now going to divide by this formula. Now be careful because since I didn't simplify it already, I do need to put parentheses around it. It's going to be 2.5 divided by the square root of 10. And so that's my standard deviation. I'm going to store that in a letter so that I don't have any rounding errors. So I know that my Z is now, I'm looking to see what the probability that that's greater than 4.427. And you can probably guess that that's going to be nearly impossible because a normal curve really only goes to 3 standard deviations above the mean. And so you might wonder why these are so different. Well, picking, if my average is 64.5, finding someone that's 68 inches tall is pretty far from my mean. In fact, it's over almost 1.5 standard deviations above. If I'm dealing with a sampling distribution, then the spread is shrinking. And so more of my population is going to be less than 68 inches high. And I think I put a little dot on here that I don't mean to be there, so let me erase that. Okay, and so I'm going to go ahead and calculate the normal CDF. And I'm going to go ahead and just use my previous answer, which I stored in letter A. My upper bound is 9999999. And since I'm dealing with a z-score, I'm going to let the calculator just use its mean of 0 and standard deviation of 1. And it's essentially 0. 4.77 times 10 to the negative 6 is essentially 0. And that makes sense. And then finally in part C, it says which of the 2 density curves represents the population and which represents the sampling distribution. Well, the population is going to be much more spread out. The sampling distribution is going to be narrower. The spread is going to be much smaller, much narrower. Okay, so what I'd like for you to do at this point, I think there are several more examples, 2, 3, yeah, so there's 3 more examples. And what I'd like you to do is go ahead and think about them. And I'm going to go ahead and ask you to press pause, complete the 3 examples, and then when you're ready, press play again, and I'll have the answers for you. So go ahead and press pause. Okay, hopefully you guys had a chance to do those 3 examples. I just want to go over the answers with you before you get started on your homework. So in number 2, it says the scores of individual students on the American College Testing Composite College Entrance Exam, that's the ACT. We know that to have a normal distribution with a mean of 18.6 and a standard deviation of 5.9. At Northside High School, 76 seniors take the test. If the scores of the school have the same distribution as the national scores, what are the mean and standard deviation of the average, the sample mean score, for the 76 students? And then again, it asks, do your results depend on the fact that the individual scores have a normal distribution? So in this case, the mean of my sampling distribution is going to still be 18.6, and the standard deviation is going to be 5.9 divided by the square root of 76. And that's assuming that the population is at least 10 times the size of my sample. That's where the 760 came from. You do have to write that on your paper in order to get full credit. You may or may not be prompted to list your conditions, so that's something that you have to understand is required in order to proceed. The mean and the standard deviation themselves don't depend on the population having a normal distribution. If I wanted to start calculating probabilities, then X bar would need to be normal, or I'd have to know the distribution of X bar in order to proceed. And in this case, I can say that X bar will have a normal distribution regardless of the population distribution because the sample is large, because it's over 30. So even if it didn't tell me in the problem that the ACT scores were normally distributed, in this case, I know standardized test scores are, it's safe to assume that they're normal, but let's say I wasn't talking about standardized test scores. Let's say I was talking about something else and I wasn't sure if it was normal. It wouldn't matter because my sample size is large. So I could continue using the normal curve for my sampling distribution. In number 3, it says an automatic grinding machine and an auto parts plant prepares axles with a target diameter of the mean of 40.125 millimeters. The machine has some variability, so the standard deviation of the diameters is 0.002 millimeters. The machine operator inspects a sample of 4 axles each hour for quality control purposes and records the sample mean diameter. What will be the mean and the standard deviation of the numbers recorded? Again, the mean of my sampling distribution is going to be the same as it is for the population, 40.125 millimeters. Don't forget to use units when you're dealing with mean and standard deviation. We didn't need to use them with a proportion. The standard deviation is just going to be the standard deviation of my population divided by the square root of 4, which is going to end up being 0.001 millimeters. So suppose the machine operator selects a sample of 4 axles that have a mean diameter of 40.128. I can see that that's slightly higher than what the mean is supposed to be. He wonders if this value is large enough to suspect the machine may need to be recalibrated. And to check his assumptions, we want to know the probability of distribution of X bar, because what he'd probably try to do is find the likelihood of finding a value of gathering a sample that large, knowing the sampling distribution. And so we'd need to know what probability distribution that we could use. Is it normal, binomial, geometric, something else, whatever? Is it reasonable to use a normal distribution here? Well, in this case, the sample is very small. Taking a sample of size 4 is pretty dangerous. However, since it's reasonable to assume that the distribution of the population of diameters of the axles is normal because it's a production process, then it's okay to use a normal distribution for X bar. So we would be able to proceed and use the normal distribution to calculate probabilities. And then in the last one, and you're again going back to the ACT score distribution where we know the true mean and we know the true population standard deviation. If I wanted the probability that a single student randomly chosen from this group or from this population gets a score of 21 or higher, again, I'm going to define my variable X to be the student score on the ACT. X I already know is distributed normally with a mean of 18.6 and a standard deviation of 5.9. So at first I'm trying to find the probability of a single student. So I'm using an X to represent a single person. I convert it to a Z-score, and that's my probability. In part B, though, we're looking at a simple random sample of 50 students and trying to figure out if the mean of that group is going to be 21 or higher. And again, we can see that there's definitely a difference between the true mean and the sample mean. The question would be, how likely is that? And I know that the standard deviation is going to shrink a lot when I increase my sample size. So in this case, X bar, I'm defining X bar to be the mean ACT score in a group of 50. So again, I'm defining my variable. Since the population is normal and the population is more than 500, I know that X bar is normal. That's because the population is normal. I also have a large enough sample, so that would be another way to say it. The reason I have to say that the population is at least 500 is because it has to be at least 10 times the size of my sample in order to use the standard deviation formula. And again, now we're calculating the probability, but this time we're doing it with X bar. And so I wrote it out because I don't have a symbol in this program to be able to put a bar over the X. It's going to be a lot less likely for me to have a group of 50 people with this high of a mean than just choosing a single person, because the extreme values are going to get absorbed in the mean. The standardized test score now you can see is 2.876, so that's a lot further from the mean than before. And so the likelihood of having a group mean being this high is very small. It's 0.002. So an inference question that will be asked maybe later is, if this is the population distribution and I took a mean sample of 50 from my school, would this indicate then that the students at my school do better than the average? And so if I take my random sample of students at my school and I find that the likelihood of seeing this value, this mean, is so rare, that gives me evidence to conclude that there's something different about the group of students at my school than the population at large. So I could conclude here that we have evidence to suggest, or actually to conclude, that students at my school do better on the ACT than nationally. And that gets us into some inference questions, which we'll be answering this semester. So I hope this kind of put some things together for you. So just to kind of summarize, you have to be able to find the mean and the standard deviation for the sampling distribution of X bar. Make sure that you check to check the 10% condition that the population is more than 10 times the sample size. And again, that's just to use the standard deviation formula. You want to understand how the shape of the sampling distribution is going to be affected by the population as well as the sample size. So X bar will be normal if my population is normal, or if my sample is at least 30. So those are the two criteria needed to be able to use a normal distribution. If the criteria is met, then you do want to be able to use a normal distribution to calculate probabilities. All right, that is it for notes today. I hope that this makes some sense. What I'd like you to do now is to go ahead and begin your homework. I don't know if you'll have time to finish it in class. If you do, you can certainly leave it. If you need to finish it up for homework, you can go ahead and turn it in next class. And I'll go over both the distribution for proportions as well as the distribution for means. We'll do a review day and then expect a quiz the following class period. So in 2 classes, we'll have a quiz. Thanks very much and good luck.